First of all, I'd like to thank you for giving me the opportunity to give the presentation, and good afternoon all. So I'm going to present our work explaining the performance of collaborative filtering methods with optimal data characteristics. We did our work with me and my advisor, Dr. Marwan Bikdash. He's not here, but I would like to thank him in the beginning. So let me start with the general introduction to the recommendation system. So it is basically, as we all know, the algorithms of the recommendation systems like presents to a target a list of possible items. I mean, to be purchased. It could be books, it could be recommending hotels, it could be recommending movies. So these algorithms of recommendation system do that. The recommendation systems can be classified mainly into two types: content-based recommendation system or collaborative recommendation system. In content-based, usually the algorithms will look at the features of the users and items they relate, like if they are similar, and the recommendation is made. In collaborative recommendation system, the historical preferences means how the users have rated the movies, how rated the items. Based on those things, collaborative filtering system makes the recommendation system. And if we combine both of the techniques, it is a hybrid filtering recommendation system. Continuing with collaborating filtering, it could be further divided into memory-based and model-based recommendation system. In memory-based is simply if like user-based and item-based. In this one, more mainly similarity between the users and items will be seen. And in model-based recommendation system, it uses the techniques of matrix factorization, like SPD and non-matrix factorization, those stuffs, and clustering based methods, and many models are being like developed regularly. Okay, and like I said, collaborative filtering system uses the rating or preferences of the users towards the items. Currently, in simplest form, the rating data is presented in like collected or prepared in terms of user item rating matrix, where users will have rated the items. I mean, they will not have all rated the all items. So the goal is to predict the ones that are not rated by the users, right? So in simplest form, it is the representation, and rating data can be discrete form like 1, 2, 3, 4, 5, or it can be 1 to 100, or it could be bipolar only, positive, negative, or by positive, negative, and neutral. So it could be many things. As we all know, the increasing data is always increasing with millions of users and items, and significant computational cost is there, obviously. And as I said, if we have rating matrix, for instance, if we are considering hotel and rating matrix for each aspect, 6 aspects of food of hotel, location of hotel, if we divide that, we can say aspect matrix and consider it as tensor also. So it could be sentiments also. Main thing, I mean, going on to the topic, what we are trying to discuss here is rating data characteristics. So based on the rating matrix, what are its characteristics? So mainly, in simple terms, it will be related to users, items, and density of the rating matrix usually. But I mean, if we derive other properties like shape of user item rating matrix, I have like given the reference. He has mentioned more than this one. I just presented the most common one that we can see: Gini item, Gini user, standard deviation in the rating. So what is the standard deviation in the rating? Number of ratings per user, which we have termed it as information per user, and number of ratings per item, information per item. So, and the motivation behind the work is like when we have different domain, there can be, like I already said, the rating scale can be different. And different, meaning the rating data characteristics will be different. If the size changes, if the rating scale changes, the rating data characteristics also going to change. Even in the same domain, the data is growing. So users increase, items, that will change the rating data characteristics. And when the rating data characteristics changes, since the collaborative filtering methods, primarily they use the rating to predict the rating matrix to predict the ratings, so their performance is going to change. If we change the data characteristics, their performance is going to change, right? Even I was talking about the huge data, like millions of users and items. It is very hard to compute, and to compute, we subsample randomly or perform those kind of stuff. So it changes the rating data characteristics, and again that affects the performance. So the goal is to, I mean, there have been studies to see when there is change in the rating data characteristics, So how can we explain the variation in the performance of an recommendation system, mainly collaborative filtering algorithm, based on the change in the rating data characteristics? I mean, the studies have been performed, but usually six or more than that, like around 10. So based on those 10 variables, we are able to explain the variation in the performance of the methods. So now we are trying to find, is there a way we can, like with minimum number of rating data characteristics, can we explain the variation in the performance? So for that, we used 1 million MovieLens data, 25 million MovieLens rating data, Yahoo using rating data. They had different rating scale and stuff, and so that we can perform the study in variety of the rating scale. So what we did was, I mean, we were running 1 million MovieLens data. It would be a very challenging thing. So we sampled the data, around 3,000 rating matrices from each, making sure they have different rating data characteristics, and perform the study based on that. And these are the collaborative filtering algorithms. Basically, we use the surprise recommendation system, the model library, and from that we use 7 of the collaborative filtering recommendation system to see how the change in the rating data characteristics affects their performance. And in standard machine learning procedure, right, we split into training and test set, launch the prediction formula for using the train set and predicting the test set to measure the performance. And for in recommendation system, root mean square error, the prediction of rating is a common one, and we define the performance as the inverse of the root mean square error. So basically, we are trying to see how the performance changes when the rating data characteristics changes, and is there minimum way we can explain the variation using the minimum number of characteristics. So first, we did multiple experiments with different rating data characteristics, but eventually we are able to find that. So when we add constant information per user or number of ratings per user, the change in the performance is linear to information per item. So for all the, I mean, the scale is different, but the nature for each of the collaborative filtering algorithms is linear. So same thing happens when we put constant IPI and change the information per user, the change in the performance is linear. So based on this, we perform regression analysis, and we are able to see, based on the adjusted average square, a significant amount of the variation in the performance of each of the algorithms. We are able to explain based on this using this equation. So information per user and information per item. So using those characters only, we will be able to explain the variation in the performance with the change in these characteristics. We might not, I mean, the studies still we need to do more, but these preliminary results, so that those will be enough to explain the variation. We don't need to use more than 6, 7, or 10. And yeah, continuing, what we did was the spatial derivative of that, right? The rate of change in collaborative filtering performance for IPU is inversely proportional to the information per user. Same thing for the information per item. And when we say a condition, what happens when IPU is equal to IPR, meaning number of ratings per user in a user item rating matrix equals number of ratings per item in the rating matrix, then it will be quadratic in IPU or IPR, information per user or information per item. So mainly we found that. So we will be able to, with the more study, with the more experiment, we will be able to find out that using two rating data characteristics, number of ratings per user, number of ratings per item, which we have found as information per user and information per item. For most of the CF algorithms that we studied 7, we can explain the variation that is happening due to the change in the change in the user item rating matrix. Again, for a square URM, meaning when IP equals IPI, CF algorithms the performance is quadratic to them. And we have results beyond the other machine learning algorithms. I mean, this experiment has not been performed for other algorithms beyond this recommendation system, so that knows to be tested. And this was empirical result. Maybe there is theoretical foundation behind it. We that can be a future research topic. Yeah, I would like to thank you, my advisor, my committee members. Oh, that was the idea, research group members. And thank you all for giving me the opportunity to present. Let us discuss if you have something.